Hello, students, one and all. Good to see you. Sorry I can't be there today. Got a sick daughter at home. Staying home, taking care of her. You understand how it is. But congrats to those who finished the HSPT over the weekend. I bet that feels really good to have it done. Wonderful to have that done. For the homework that's going to be tonight, check Canvas. It'll be there after you watch this video. You may have to conclude this video for homework tonight. And if so, then that's okay, because I know we have shortened classes today due to the mass. Don't forget also next week is the unit test on all this stuff, on our systems unit. And here we have the final method to learn, and it's called Systems of Linear Equations by Elimination. As you can see right up here, we're going to learn the final of 3 methods that we're going to learn. Elimination. And it's going to be part 1 during this video today, and we'll do part 2 when I come back. So let's get right into it. We have done graphing last week. Nice job. We did substitution, practiced that a lot last week, even played a game on Friday. Now it's time to learn elimination. The final of the 3 big methods to solve a system. For those interested in learning how to use a matrix to solve a system, happy to show you that. Feel free to come Tuesdays after school, 3:30 to 4:30, for our Topics in Algebra 2 class. All right, let's get into elimination. The graphing method, as you know, is called such because to solve the linear system, that's right, you graph both equations. You got to use one of those coordinate planes. And then last week we learned that the substitution method, well, it's called that because to solve the system, you have to, that's right, substitute. That's why it's called that. In other words, remember you're a person or thing acting in serving or in place of another. You're literally replacing something with something else. You're substituting. And this meme is so true, especially today, right? As Mr. Ripe's Virtual is here with you. All right, now, remember there are kind of 2 parts to the substitution method as well. The first part to the substitution method was when one of the variables was already isolated in the system right from the start, like this example here. Notice that x was already isolated, and we could just take the 6 minus 4y and pop it right there. After that 2 there, because that's what x is. It's 6 minus 4y, and then we'd solve accordingly for both variables. And then the second part we noticed is that when, that's not always the case. When one of the variables or the other, x or y, is not already isolated. So we had to do this preliminary step where we had to choose one of the 4 variables to isolate, either x or y in the first or x or y in the second. And then we'd proceed back to how we were doing it earlier. Kind of the same thing here with elimination. There's 2 parts to it. And I'm going to go through the first part with you. All right, the part where the system's kind of already set up in that ideal way to use elimination. But before we do that, let's make sure we know what that word elimination means and why it's called this. The elimination method is called such because a pair of terms. What do you think the word is there? That's right, eliminate. And what does eliminate mean? To remove or get rid of. To omit, to remove from further consideration, to eradicate, or, ooh, that gets dark right there. Anyways, you get the idea. Things are going to go away. Things are going to get rid of. That's what the elimination method does, and it makes it really nice and clean once things are gone. Really nice to proceed forward. Come on, let's get into it. Here we go. First, got to go back to it for just a moment. We got 2x plus 3y equals 11, negative 2x plus 5y equals 13, our first system. I want us to first solve this one by graphing. Yes, let's solve it first by graphing. This is the system we're going to solve 3 different ways. Graphing, then elimination. Graphing, then substitution, then elimination. Let's see which method is kind of the most effective way of doing it. Here we go, everyone. I'm going to take 2x plus 3y equals 11, which, as you can see, is not in slope-intercept form, and I'm going to make it into slope-intercept form here. All right, give me a moment while I do that. So through the magic of editing, as you can see, I took the first equation, subtracted 2x from both sides, and then divided everything by 3, because remember, I want to isolate y. I want to put everything in slope-intercept form by isolating y. And I got this crazy equation here. Y equals negative 2/3 x plus 11/3. And while that slope is okay, I'm not a big fan of that y-intercept being 11/3. I'm just going to go right ahead and, well, make that into 3.6 repeating, which it is. And then I got to graph it. I got to graph that line. And because that 3.6 repeating is not a perfect integer, I had to kind of estimate where that y-intercept was. So I kind of put it between 3 and 4 as best as possible, just slightly closer to 4 than it is closer to 3. Made my slope negative 2/3, and I got it. All right, so now what we have to do is we have to take the other equation, which is also not in slope-intercept form, negative 2x plus 5y is equal to 13, and I have to make it into slope-intercept form. I have to isolate y. All right, I'm going to go ahead and do that right now. As you can see, I got another kind of not very desirable y-intercept. While that slope of 2/5 is okay, I'm just going to kind of get that y-intercept into a decimal. 13 divided by 5 is 2.6. All right, so once again, I have to estimate kind of where that is. Well, I know that's between 2 and 3, just a little bit closer to 3 than it is to 2, so there you go. And then I'm going to go down to, I'll go up 2, excuse me, up 1, 2, and over 1, 2, 3, 4, 5. I'll do it again, up 1, 2, 1, 2, 3, 4, 5. There we go. Get my ruler here. And hopefully I'm thinking I want these to intersect at 2 integers, because if I'm graphing these, as we saw, if they don't intersect at 2 integers, it's kind of hard to see where they intersect. And it looks like I tried to find their point of intersection as best as possible right there. 1, 3. All right, so we're going to assume that 1, 3 is the answer. But again, we see a flaw in this method of graphing because, well, what if the y-intercepts are kind of strange? Decimals, fractions, all those things that are involved don't really give you those perfectly nice, clean integers, so it's kind of hard to find the point of intersection. We're going to assume that 1, 3 is the solution here, but we're going to check our work and make sure that it is by doing it another method. Come on, let's take the same system and let's solve it by substitution. All right, so hopefully we think the answer is 1, 3. We're really hoping that it is because we want to know that our graphs are accurate. So what I'm going to do is I'm going to take one of the equations, and once again, I'm just going to isolate one of the variables. In fact, I'm going to take some of the work that I just did previously, because you notice I isolated y for both equations. I'm going to take one of those and start that way. So I took that second equation, the most recent one I just worked with, and notice that I isolated y to get it into slope-intercept form. Well, I can use that to my advantage here, so I'm not reinventing the wheel. But I don't want to work with the decimal version of it. I want to work with the fraction, complete fraction version of it. So that way, I'm doing exact numbers here. So I know that y is equal to 2/5 x plus 13/5. Now remember, the rule is with substitution, I got to take what y is, in this case 2/5 x plus 13/5, and I have to send it into the other equation's y variable. So I'm just going to go ahead and take this and pop it right into that first equation right behind that 3. All right, so let's see what I get there. I get 2x plus, and I'm going to substitute in, whoops, don't forget the 3 coefficient in front. I'm going to substitute in this whole craziness of 2/5 x plus 13/5. And of course, that is still equal to 11. Whew, and I got to solve for x now. All right, well, I'm going to take that. I'm going to distribute the 3. So I get 3 times 2/5. Well, 3 times 2 is 6. So I'm looking at 6/5 x plus, don't forget to distribute the 3 to the 13/5. 3 times 13 is 39. So I'm looking at 39/5. Remember, I'm not multiplying that 3 to the denominator, just to the numerator. And that's equal to 11. And the 2x is still in front, and so is that plus sign because that 6/5 is positive. I got to combine like terms. 2x plus 6/5 x. I'm going to do my math here. I get 16/5 x, and I still got the 39/5. That's still equal to 11. I have to isolate x, so I'm just going to go right ahead and subtract 39/5 from both sides. A lot of fractions involved in doing this, especially using this method, as we saw. All right, well, I did my math earlier, and 11 minus 39/5 is 16/5. Yeah, you're welcome to check my math on that one. To get rid of the 16/5 in front of the variable, so I just have 1x. Remember to get rid of any fraction nice and efficiently. I'm going to multiply both sides by the reciprocal. And remember, any number times its reciprocal is nothing more than 1. That's right. So I'm seeing that on both sides here. So I see that x is equal to, well, 1. Oh, so I did get the same x coordinate as when I graphed it. X was equal to 1, which hopefully means y is equal to 3. Let's find out. I'm going to take this 1, which is x, and I'm going to plug it into one of the two equations. Remember, it doesn't matter which one. You know what? I'm just going to go right ahead and use that first one again. Put it behind that 2, because remember, x is equal to 1. So now to finish this off, I got 2x plus 3y is equal to 11. I'm going to erase x and replace it with a 1. And we think it's 1, 3 from graphing. Let's see if it is if we do it algebraically. Let's see here. We got 2 plus 3y is equal to 11. I got to subtract 2, and look at this. 3y is equal to 11 minus 2, which is 9. Divide everything by 3. Y is equal to 3. Yes, so the solution was 3. And we did get it by graphing, and we did get it by substitution. So nice work, but there was a lot of fractions involved in both of them, and decimals for the graphing one. And you notice that with the graphing, we were kind of hoping it was 1, 3. Unfortunately, it was. With substitution, we're able to confirm that it's 1, 3, so that's nice. But was there a way we could have done this maybe without having to do all sorts of that work? I mean, each method for this system took a while. There must be a more effective way of solving the system. Graphing method, as we know, it's useful when both equations are in slope-intercept form, which for our system, that was not the case. And substitution method is useful when one equation has a variable already isolated, which wasn't the case for this system either. You see, this system didn't have any of those things. So do we ask ourselves, slope-intercept form, should we isolate a variable? But here's the thing, both of them, both equations, are in standard form, both of them. And when that happens, let's try using the elimination method. When you hear the word eliminate, what number do you think of? Think of it in your head. Give yourself a second. Not 1, not -1. That's right, the only number that's not negative nor positive. When you hear the word eliminate, I want you to think of the word 0. The number 0, rather, which is a word, of course. -3 plus 3, that's 0. 3's are gone. -3y plus 3y, hey, that's 0. 4 minus 4, yeah, we know that's 0 since kindergarten. 4z minus 4z, well, that's also 0. And what do we add to 9 here? -9 to get 0. Well, that'd be a positive 9, right? It's opposite negative and positive 9. Well, what do we add to -9b to get 0? Well, it's opposite, positive 9b. Remember, opposite means positive, negative, positive. Flip the signs. That's what opposite means. And this is an important concept. When you're trying to get rid of things, aka eliminate, you need opposites. All right, so now another kind of strange question that seems out of the ordinary, but it's going to make sense in a moment. If you were asked to add 3,926 and 813, let's say you're back in like 2nd grade and you're adding these two things together, and your teacher said, yeah, I got to show all of your work and you got to write it down. How would you write it? We'll get the solution in a moment. We'll get the answer. How would you write 3,926 plus 813? Would you do this? 3,926 plus 813. Would you write it horizontally like that? Probably not. We learned the best way to do it is to take those two digits and stack them on top of each other. I want to assume that most people in this room, most people watching this video, would take that 813, put it right below the 3,926. Then you'd probably draw one of these lines here and put a little plus sign in the corner there, right? Now, why did we do it that way? Because of place value. The 6 and the 3 are in the 1's place value, so we stack them on top of each other. The 2 and the 1, those are in the 10's place value, so we stack them on top of each other. The 9 and the 8 are in the 100s, so we stack them on top of each other. And the 3 in the thousands place value, just kind of hanging out by itself, technically above a 0, right? Technically. And then you might recall, okay, 6 plus 3 is 9, 2 plus 1 is 3. You just add down the columns, down the place values. 9 plus 8, that's 17. So what we're going to do is carry the 1. 3 plus 1 plus 0 technically is 4, and the answer is 4,739, right? We stack them on top of each other vertically to add them together. All right, why are we reviewing that, Mr. Ripes? That's from long ago. It's because this is what we use for the elimination method. You stack digits having the same place value on top of each other. Yeah, as we just did. Elimination method uses the very same idea. However, we're not going to align place values. We're going to align like terms on top of each other vertically. That's right. In other words, stack the like terms. Here's the system again, the same one. We know the solution's 1, 3. Let's see if we can get that same solution a lot more efficiently using elimination. The 2x and the negative 2x, those are like terms because they both have an x. The 3y and the 5y, those are like terms because they both have a y. And of course, the 11 and the 13 are constants, not having variables. So therefore, we stack those on top of each other. Whoops, sorry about that. We stack those on top of each other. All right, so what we're going to do now is we are quite literally going to do what we just did. We're going to add them together. And you can add entire numbers together, you've known, but you can add entire equations together. That's right. We're not going to modify any of these equations in the system as they are right now. We're going to leave them, and we're just going to draw that big old line and put that little plus sign in the corner like we know to do for a long time. And I'm going to add down the columns, down the place value, quote unquote, the like terms in this case. Help me out, everyone. 2x plus negative 2x is 0. Those eliminate, right? 2 plus negative 2 is 0. So 2x plus negative 2x is 0. So those are gone. Don't even write anything. Don't write 0y, don't write 0x, don't write anything. But we still got to keep going here. 3y plus 5y. 3y plus 5y. Oh, that's 8y. Okay, and 11 plus 13. All right, well, that's 24. And of course, still bring down that equal sign in the middle. And look at this, we got 8y is equal to 24. Well, you've known how to solve this for a long time. Divide both sides by 8, and y is equal to 3. That's the same 3 that we got when we used substitution and graphing. Well, we got it a lot easier. So we have F the answer because we eliminated the x terms. Well, how do we get the other part of the answer? Because we know the answer, of course, is 1, 3, and we only have part of it. How do we get that 1 there? Well, we go back to the previous method. Here, take this 3, which we know is y, and let's substitute it. So this kind of method uses two methods. Let's put it back into that first equation. So we got 2x plus 3y. We're putting it back into the original equation. Imagine the 2x's are back there, and we're going to replace that y with a 3 equal to 11. And let's see if we get 1 for x as we got before. 3 times 3 is 9. Oh yeah, look at that. We're going to subtract 9 from the 11, and we get 2. And if 2x is equal to 2, well, then x is equal to 1. So we still got 1, 3. Look, so much more efficient. That was great. That didn't take long at all. We eliminated some terms, and this is the process that we have to get down and get understood. Now, once again, just to emphasize a point here, to get that x for 1, what if somebody said, no, I don't want to pop that 3 into the first equation? What if I want to do in the second equation? Will I still get the same positive 1 as before? Check this out. We're going to replace the y with 3 this time, and let's see if we still get the same 1. So negative 2x plus 15 is equal to 13. I'm going to subtract the 15 from both sides. I get negative 2x is equal to 13 minus 15, and look at that. X is still positive 1. So no matter where you substitute it back in, you're going to get the same answer as long as your math is accurate. Do you have to do it twice? No. Why did Mr. Ripes just waste our time doing it twice? Well, to show you that you can do any equation. As long as you're sending it back into the original equation. The original equation. No terms have been eliminated when you put it back into the original equation. Let's do another example. Because as we can see, elimination is quite nice from this first example. Here we go, everyone. Note that the terms with the x variable eliminated, this is the very idea. Either the x variables or the y variables will completely eliminate if you choose wisely. What do I mean by choose? You're going to add or subtract. That's the idea. You're going to add or subtract the two linear equations together with the intention that a pair of like terms zero out, aka eliminate. And if you can add two linear equations together, you can certainly subtract. Here's our next one. Let's get this one in our notes here. Negative 5x plus 2y equals 22. 3x plus 2y equals negative 10. Let's start by trying to add the two equations together first. Let's see if we add them together, will a pair of terms eliminate? Let's see here. Don't start writing in this note yet because I'm going to do something wrong here. Negative 5x plus 3x. Well, if I add those together, do I get 0? No, I get negative 2x. And 2y plus 2y, if I add those together, do I get 0? No, I get 4y. And 22 plus negative 10, if I add those together, do I get 0? No, I don't. I get 12. So nothing eliminated when I added. Well, if addition didn't work, let's get rid of that, then maybe subtraction will. All right, so let's try this. Negative 5x, careful with this, negative 5x minus 3x. Negative 5x minus 3x, that's negative 8x. 2y minus 2y. The y terms cancel out this time. Because you notice how the two y terms match up? 2y minus 2y? That becomes 0. I'm subtracting them. And careful, 22 minus negative 10. That's not 22 minus 10, that's 22 minus negative 10. That's positive 32. It's like saying plus 10. And look, I just have this little tiny one-step equation here that to solve for x, I just need to divide both sides by negative 8, and x is equal to negative 4. Beautiful. So I have half the answer. I know the answer is negative 4 comma something. Well, to find out what that y-coordinate something is, let's go ahead and take that negative 4, and you choose which equation to pop it into. I'm just going to go ahead and put it back into the first one. You can put it into either. So negative 5 is going to be multiplied by a negative 4. I'm replacing the x with a negative 4, plus 2y is equal to 22. So 20 plus 2y is equal to 22. I'm going to subtract 20 from both sides. 22 minus 20 is 2. Y is equal to 1. So negative 4, 1. We got it. We got it with a very efficient manner. Elimination. Works well. The question may still remain, though. How do I know to use addition or subtraction? I mean, is there a way to look at the system and determine that? Well, there is. And let's kind of practice that before we solve these last few systems here. Here I have a few examples here. And the question is, do I add or do I subtract to get 0? Notice that 0 is my solution for each of these. If I have a 19 and another 19, both of them positive, if I add them together, do I get 0? Of course not. 19 plus 19 is not equal to 0. 19 minus 19 is 0. And if I have a positive 6 and another positive 6, if I add them, will I get 0? No, of course not. If I subtract them, I'll get 0. And what about a negative 3 and another negative 3? If I add them, will I get 0? No, if I add them, I get negative 6. If I subtract them, I get 0, right? Because negative 3 minus negative 3 is like saying negative 3 plus 3, isn't it? Same thing with 2 negative 10s. If I add them, I don't get 0, but if I subtract them, I do. So when the signs are the same, we notice that all of these had the same sign. Both numbers were positive or both numbers were negative. We had to subtract to get 0, didn't we? You might see where I'm going with this. If I have two of the opposite numbers, 19 and negative 19, if I add those, I get 0. Negative 6 and positive 6, if I add those, I get 0. 3 and negative 3, 10 and negative 10, if I add them, I get 0. So when I have opposite signs, remember opposite means one's positive, one's negative, you add them. Sorry, I was about to write a subtraction. You add them together. All right, so when the signs of the terms are the same, you subtract. When they're opposite, you add. Here we have 4 systems here. First, before we solve them, let's determine which terms are going to cancel out and if we're going to add or subtract. And then we'll solve them. Here we go. Let's take this first system right here. Which terms are going to kind of cancel out? The x terms or the y terms? Well, look for the terms that somewhat match. They might not match in every way, shape, and form, but they'll have a same digit. And maybe the signs might be the same, and maybe they won't. And look to this here, everyone. We notice that this has a 3. Oops. This one has a positive 3y, and a negative 3y. Those are the matching terms. They both have a 3. One's positive, one's negative. If you add them, will they become 0? Yeah, they will. If we add them, they'll become 0. Okay, so we know we're going to add those terms together to make those y terms cancel out. We'll come back and solve that one in a bit. Let's just determine if we're going to add or subtract them first. And the one next to it with the 7x minus 2y equals 5, and the 7x minus 3y equals 4, which terms are going to cancel out this time? The x terms or the y terms? Yeah, you're right. The x terms are going to cancel out because you notice how they both have a 7? All right, and those 7s are both positive, aren't they? So if I add them, will I get 0? No, but if I subtract 7x from 7x, then I'll get 0. So I know for that system I need to subtract. So I'm just going to mark that down there. And we got 2 other systems here. Let's see here. Negative 5x minus 6y equals 8, 5x plus 2y equals 4. It appears that the negative 5x terms and the 5x, those are going to cancel out because those match slightly. One's negative, one's positive. Oh yeah, I'm going to add those together. Very, very good. Very good. And the last one here, which terms are going to match up? The x terms? No, the y terms. Look, those have a 4's involved in one way or another. And a 4 and a negative 4, if we add them together, because those are opposite signs, right? Opposite signs. Add them. Opposite signs. Add them, right? There's technically a plus sign there. All right, nice. Okay, so we know which ones we're going to add or subtract together. We got these 4 different systems. Let's take one of these together here. Here, let's take this one. Let's take this one together here. Let me get rid of all that. Let's go right back to where it started. We know we're going to add them together because that was a negative 5x to start here. Negative 5x plus 5x. That's 0, right? Negative 5 plus 5. Negative 6y plus 2y. Careful with your math there. That's going to be, of course, negative 4y. Is equal to 8 plus 4, which is 12. Oh, well, if negative 4y is equal to 12, then I know with 100% certainty that y is equal to negative 3, and I already have half my answer. Isn't that great? All right, now how do I get the x-coordinate? Substitution. I'm going to take this negative 3, and, oh, what the heck, I'll put it behind that 2. Again, you can choose. So I've got 5x plus 2y is equal to 4. I'm going to erase the y and replace it with a negative 3. Let's do the math here. 5x minus 6 is equal to 4. 5x is equal to 10. X is equal to 2. Whoa, my solution is 2, negative 3. There it was. Didn't have to graph. Didn't have to substitute until I knew one of the variables. I'll do one more with you. Eeny, meeny, miny. Let's do this. Let's do this first one here. Oh, I got to add these again. Careful with your math here. 4 plus negative 2. Careful. 4 plus negative 2. Negative 2x. Negative 3y plus 3y. Gone. Eliminated. 5 plus negative 7. Negative 2. Oh, x is equal to negative 1. I divided both sides by negative 2, which I know many of you can do mentally, which is great. I'm going to take that negative 1. I'll do the second equation again, right there behind that negative 2. Let's see here. Negative 2x plus 3y is equal to negative 7. Let's get rid of that x. Erase and replace it with a negative 1. 2 plus 3y is equal to negative 7. I'm going to subtract 2 from both sides. 3y is equal to negative 9. I subtracted 2 from negative 7. So y is equal to negative 3. When I divided both sides by 3, my answer is negative 1 comma negative 3. Impressive, everyone. As you can see, elimination works very, very nicely. It's nice and clean, it's nice and efficient, and not much work involved. Definitely a fan favorite. You got 2 more systems here. The second one and the fourth one. I invite you to try these. I want you to work on these in your notebook. After you're done with them, check the solutions, okay? Pause the video now. When you're done, unpause it. Let's see if you got the solutions. Go for it. Did you get 1-1 for the second and 5-4 for the fourth? If you did, hey, nice job. You are in really good shape for elimination method, part 1. All right. To close up this video, let me say this, everyone. This was just part 1. What if you add or subtract both equations, but no pair of terms eliminate? Like, look at this system here. Let's see here. If I were to add them together, the x terms wouldn't eliminate because that makes 7x. The y terms wouldn't eliminate. That makes 9y. And of course, the constants wouldn't eliminate. We never want the constants to eliminate. Oh, so Mr. Ripes, if addition didn't work, then subtraction would work. Well, let's see here. 5x minus 2x. That's not 0. 6y minus 3y. That's not 0. So can we not use elimination here? Do we have to use substitution or graphing? No, we can still use elimination, but we have to do a preliminary step. But that preliminary step, I'll have to teach you when I come back on Wednesday, okay? Remember, there's no class tomorrow because we are going to see A Christmas Carol. So I hope this video helped you. If you need help throughout the day, I am available for you, all right? Just email. I'll be on Zoom. There's Math Lab in the evening. Everyone, thanks for watching. Check Canvas for your assignment. Have an awesome Monday.